might get close, sometimes really, really close.
But never perfectly precise.
Exactly. It's kind of like being asked to measure the exact distance to the moon, but not just, to the nearest mile, but down to the nearest millimeter.
Wow.
But with tools that were only ever designed for, well, rough estimates. It seems like a proper mathematical Everest, doesn't it? A challenge that, by all accounts of classical algebra, should resist any attempt at a perfectly precise symbolic answer.
And that's precisely what we're diving into today, Ezouidi's theorem. What we found in the source material suggests this is a true game changer, a method that, and I'm quoting here, redefined how we solve high-degree polynomials. It feels like finding, I don't know, a secret tunnel in a mountain everyone thought was just solid rock.
That's a really powerful analogy, actually, because what's truly fascinating here, the core of it, is that this isn't just about finding, say, better approximations or a slightly sharper guess.
Right.
Our mission in this deep dive is really to unpack how this theorem lets us derive exact symbolic solutions for polynomials that traditionally pose significant challenges. We're talking about pure, unadulterated precision.
Exactly. And to really get a feel for the depth of this breakthrough, we're going to walk you through a couple of, well, frankly, incredibly intimidating examples. First, a truly monstrous 17th degree polynomial one that would make most mathematicians just instinctively reach for their approximation tools.
You bet.
And then, just to sort of push the boundaries even further, we'll touch on an 18th degree one. And that's where Ezouidi's theorem reveals this almost, I don't know, magical simplification.
It's quite something.
Our goal is for you, listening, to truly grasp the power of this approach compared to those classical methods that, despite their usefulness, have always fallen short of perfect exactness.
Yeah, absolutely. So you, our curious learner, you'll hopefully gain a shortcut to understanding a pretty groundbreaking mathematical concept, complete with some surprising facts about what was previously thought impossible, and just enough detail, we hope, to keep you hooked without feeling, totally overwhelmed. It's about seeing how these centuries-old limitations might just be, well, evolving right before our very eyes.
Okay, so we've hinted at these impossible problems. But before we jump into the solution, maybe we should define our adversary a bit more clearly. Like, what exactly is a high-degree polynomial, and why has it caused so much trouble for so long?
Good idea. Let's set the scene.
So let's really set the stage by understanding this mathematical beast we're talking about. High-degree polynomials. At its heart, right, a polynomial equation is just an expression. It's made up of variables like x and numbers, which we call coefficients, and they're all combined using, basic stuff, addition, subtraction, multiplication, and these non-negative integer exponents. Think of something simple like x set plus 2x plus 1 equals 0.
Right, a quadratic, familiar territory.
Exactly. And the degree of that polynomial is just the highest exponent of the variable in the equation. So x set plus 2x plus 1 equals 0 is a second degree polynomial. Simple enough.
And this degree, it's absolutely crucial. It tells you how many roots or solutions the polynomial typically has. So a second degree polynomial, like the one you just mentioned, it'll have 2 roots.
Right.
A third degree or a cubic will have 3, and so on. The higher the degree, the more roots there are to find, and generally the more incredibly complex it becomes to solve.
Yeah.
Especially if you're aiming for those elusive, exact, symbolic solutions rather than just, approximations. The interplay between all those terms and their coefficients, it just escalates really quickly into something very, very difficult to untangle precisely.
Okay, to give you a real sort of visceral sense of this challenge, let's introduce our first specific example. Imagine an equation just stretching across your entire mental whiteboard, right? 17 different terms. This is a 17th degree polynomial. You can almost feel the weight of its complexity. But 17O plus 183O's second 3. Plus 17 19730 plus 730 plus 783SO. So 1987 Say Carl Nudo plus 730 over 1060 plus 746 plus 619 200 no plus 437 546. I don't know.
Wow. Yeah, just looking at that, even if you're not actually trying to solve it right now, you can appreciate the sheer length and the staggering range of those coefficients. Yeah. Like, the coefficient for by 16 is 18, which seems reasonable enough. But then the coefficient for by 6 leaps to over 1.7 million.
Whoa.
And the constant term at the end, L16Q, is negative 437,553. The coefficients themselves just swing wildly in size and sign. It's visually intimidating, definitely. And computationally, well, for traditional methods, it represents a really profound challenge.
So, okay, you look at that monster, and my first thought isn't even how do I solve it? It's more like, how on earth did someone even write that down?
Hmm.
Is there a specific part of that equation that mathematicians would traditionally just sort of throw their hands up at? Like, what stands out to you as the biggest hurdle here for finding all 17 exact roots?
That's a really good question because it's not just the length, right, or the sheer number of coefficients, though that's part of it.
Right.
It's the intricate interplay of all those terms. Each one has its own influence on the potential roots. For me, the biggest challenge is the inherent complexity of finding all those roots simultaneously and precisely. Each root could be a real number, or it might be a complex number, involving imaginary parts. And with 17 of them, each potentially affecting the others, the traditional methods just quickly become either computationally overwhelming or more critically, they're just inherently incapable of giving you exact values.
Incapable. Uh-huh.
Yeah, it's like a multidimensional puzzle, and each piece affects all the others in ways that are incredibly difficult to isolate perfectly.
Right. Okay, given that level of complexity, it really begs the question, what tools were scientists and engineers using before something like this theorem came along?
Hmm.
And that brings us to the traditional toolbox that mathematicians have relied on for centuries.
Hmm.
When they're faced with these high degree polynomials like the 17th degree beast, historical approaches, as the source says, often involve numerical approximations. These are methods basically designed to get you close to the answer, to give you a good enough estimate.
But not perfectly to the answer.
Exactly.
Yeah, think of methods like Newton's method or maybe the bisection method. These are iterative processes. You start with an initial guess and then you refine that guess through a series of calculations, getting closer and closer to a root with each step.
Okay.
And they are absolutely indispensable for many practical applications, don't get me wrong, especially when an exact analytical solution just isn't available, or maybe it's just too cumbersome to compute.
Right.
But they come with a fundamental limitation.
And that limitation seems critical, especially when you think about what we're trying to achieve today with this theorem. They give you approximations of the roots, not the exact values,
Correct.
which means, as the source points out, they come with the risk of rounding errors. Every step in the calculation, every decimal place you chop off, every little truncation, it introduces a tiny potential for error.
Hmm. And in a long, complex polynomial like that 17th degree one,
Yeah.
these tiny errors can accumulate really rapidly. They can compound with each iteration, so they can't guarantee exact values, period.
So if you're working on something where absolute, like pristine precision is paramount, say, certain areas of cryptography.
Oh, definitely. Where a tiny error could compromise an entire security system.
Right. Or designing highly sensitive engineering components like the precise trajectory for a spacecraft. Maybe.
Or even in fundamental physics, where an exact value might unlock a whole new understanding of the universe.
In all those cases, these approximations just fall short. They give you a good enough answer, maybe, but not the true precise answer.
Exactly. And this really highlights the gaping need for a fundamentally different approach, a pathway to perfect precision.
Okay, and here's where it gets really interesting and maybe, I don't know, a bit controversial in the math world.
Yeah.
Because we have to confront what has been, for nearly 2 centuries now, a cornerstone of algebra, Abel's impossibility theorem.
Ah, yes, Abel.
This theorem famously states that certain polynomials cannot be solved using radicals. And what does using radicals mean exactly?
Yeah. It basically means you can't find their solutions by a general formula that only involves basic arithmetic operations. Adding, subtracting, multiplying, dividing, and roots, like square roots, cube roots, fifth roots, things like that.
Okay.
And this applies specifically to polynomials of degree 5 and higher, so quintics and above.
Wow. So for nearly 200 years.
Yeah, this theorem has profoundly influenced how mathematicians perceive the limits of finding exact solutions. It essentially said, look, for polynomials of degree 5 or higher, don't waste your time trying to find a universal formulaic solution like the quadratic formula works for degree 2 polynomials.
So it just shut the door.
Pretty much. It implies that for many high-degree polynomials, seeking an exact symbolic root might indeed be a futile exercise. It really closed the door on a whole class of problems, or at least on finding that kind of general formula. It directed mathematicians towards other avenues like numerical approximations or maybe focusing on very specific solvable cases.
Okay, hold on to your hats because here's the real aha moment from the material we've been deep diving into.
Okay.
It boldly states that Ezouidi's theorem, and I quote again, contrary to Abel's assertion, does demonstrate that even polynomials with radical roots can be solved exactly.
That is a monumental claim.
Right. It suggests a breakthrough beyond these established limitations, something that has the potential to fundamentally shift our understanding of algebraic solvability.
It definitely raises an important question. If a new method can indeed provide precise, solvable roots for polynomials that would otherwise be deemed unsolvable, problems that have been considered impossible for generations, what does that actually mean for the fundamental boundaries of mathematics as we know them?
Yeah, what does it mean?
Well, it suggests perhaps a new paradigm, moving beyond the historical constraints that have shaped algebraic thought for so long. It might be less about, say, breaking a rule and more about discovering a new rule, or maybe a deeper, more intricate structure that we just hadn't perceived before. It could really change how mathematicians even approach problems, maybe encouraging them to look for exact solutions in places where they previously would have just settled for approximations.
So it's not just some academic curiosity then.
Mm.
If Abel's theorem has told us for centuries, nope, can't solve those high degree ones with a nice formula, and Ezouidi's theorem comes along and says, well, hold on, maybe some of them, maybe even all of them in a different way. It really is like finding that secret tunnel in the mountain.
Exactly.
So what does this actually mean for those otherwise deemed unsolvable equations? Let's unpack the theorem itself and see how this new paradigm actually works.
Let's do it.
Okay, so what's the fundamental difference here?
Well, at its core, Ezouidi's theorem introduces a really fundamental difference from the traditional methods. It doesn't approximate, full stop.
Okay.
Instead, it allows us to break down the polynomial and solve for the roots symbolically. And that word, symbolically, is crucial.
Symbolic meaning.
Think of it like this. If you wanted to know the exact circumference of a circle, right? An approximation method might give you around 3.14 times the diameter.
Right, pi-ish.
Pi-ish, exactly. But a symbolic solution would give you pi times the diameter, the perfect, irreducible representation, pi itself.
Ah, okay. So instead of getting a decimal approximation like, say, 3.14159, which goes on forever anyway,
Right.
you might get something like pi itself, or maybe like the golden ratio, that expression 1 plus squared 2.
Precisely. It's about expressing the roots precisely, often in terms of other symbolic quantities or known mathematical constants, rather than just a numerical estimation that might have tiny accumulating inaccuracies. It means you have the exact unsimplified truth of the number, not just a close cousin that looks similar.
Got it. The exact truth. I like that.
And the key process at the heart of this theorem is its reliance on a recursive process.
Recursive, meaning it builds on itself.
Exactly. It systematically finds values by building upon previously calculated steps. Each new value is derived directly and precisely from the preceding ones. It creates this chain of exact calculations that leads, ultimately, to the exact roots. It's kind of like building a complex structure brick by brick, knowing that each brick is perfectly placed because its position is informed by all the bricks that came before it.
Okay, that makes sense. A step-by-step exact process.
And the engine of this exactness, the very heart of this recursive computation, is a specific central formula. The source material tells us that the formula used to compute the roots, or more precisely, the symbolic coefficients that lead to the roots, is this. Okay, whoa. That looks intense. Can we break that down a bit conceptually without getting lost in every single symbol?
Absolutely. Let's unpack the key components. First, you see terms like du ya. These are what mathematicians call binomial coefficients that adjust the terms.
Binomial coefficients, like from Pascal's triangle. Exactly like that. Think of them as special counting numbers that pop up in lots of areas of math, often in probability or when you're expanding polynomial expressions like a plus b n. Here, they essentially provide the correct weighting and arrangement for each part of the calculation as it builds up.
Okay, weighting and arrangement. Got it. What's next?
Next, there's a component that incorporates newness. This term is crucial because it helps to account for the original polynomial's degree, n, as the recursive calculation proceeds.
So it remembers how big the original problem was.
You can kind of think of it like that, yeah. It's like a mathematical memory or maybe an amplifier that ensures the calculation correctly accounts for the polynomial's overall structure at each step. It makes sure the final solution reflects the full complexity of the initial equation. It keeps the recursive process aligned with the original problem's nature.
All right, makes sense. Then there's that delta.
Right. This involves Neuerbergs. Now, no is the very first coefficient in our original polynomial, the one attached to the highest degree term, like the natus 18 in our 17th degree example.
Okay, the leading coefficient.
Exactly. It acts as a sort of anchor or a primary scaling factor, and it's adjusted by the power care, which essentially scales its influence based on which step of the recursion we're currently on. It ensures that the influence of the most dominant term in the original polynomial is correctly propagated through all the subsequent calculations.
Okay, propagating the influence. And the last bit.
This is where the recursive nature really shines. This element refers to the earlier terms in the polynomial as we proceed through the recursion.
So it looks back at the previous steps.
Precisely. Each step builds upon the results of the previous calculations, incorporating the historical context of the polynomial's original coefficients, L values, into the current calculation of the new coefficients, S values. It's like a memory function built into the formula, ensuring every step is precisely informed by everything that came before it. This leads to a perfectly coherent and ultimately exact result.
Wow, okay, so this formula, with its binomial coefficients for structure, the inner term keeping track of the degree, the initial coefficient L0Q acting as a kind of scaling anchor, and these recursive links looking back at previous terms, that's the engine. That's the beating heart of how the theorem systematically finds exact values.
That's it.
And it avoids any approximation errors because it's always working with these pure symbolic relationships. It's revealing the underlying precise structure of the polynomial to find its exact roots rather than just guessing or getting close.
It's truly a systematic unraveling. Layer by layer, it uncovers the polynomial's hidden exactness. The beauty, I think, is in its methodical, relentless pursuit of precision. It transforms what looks like an impossibly tangled mess into this series of perfectly interconnected steps.
Okay, let's unpack this then. Let's see how this recursive magic actually works in practice with our high degree polynomials. This is where we get to witness the theorem in action, right? Transforming the impossible into the precisely solvable.
Let's dive in.
So let's reintroduce our main challenge, that intimidating 17th degree polynomial. You remember it, the one with 17 terms, coefficients swinging wildly all over the place.
The Goliath.
Yeah, what looks like an impossible task to find its 17 exact roots. Just to refresh your memory, visually, it's that equation just stretching across your screen.
And remember, the traditional way to solve this would typically be through numerical approximation, which, as we discussed, comes with those inherent errors and just can't guarantee perfect precision. But with Ezouidi's theorem, we're aiming for exactness. It's a completely different philosophy, really, a different approach to problem solving.
Okay, so the core of the method, as we mentioned, involves calculating this set of symbolic coefficients denoted as naro norio.
Right, the Ziorio's values.
These are recursively calculated based on the original LQ coefficients of the polynomial. And the key, I really want to hammer this home for an exact solution, is that every coefficient is determined symbolically without any numerical approximation. It's pure, clean calculation all the way.
Absolutely. So let's walk through the process of getting these calculations. We start from K0 and we just work our way methodically up to K17, applying that recursive formula we discussed. It's a step-by-step process, sure, but each step is essential to achieve that final exact solution. And what we'll notice is this cascade of, well, increasingly large but precisely calculated numbers.
Okay, so starting at K0, what happens?
For K0, the formula for narrow stuff simplifies really nicely. It just becomes 1.
S1Q1.
And that establishes our base case for the recursion. This initial value provides the starting point for the entire chain of exact calculations that follow.
All right, step 1 done. Now for K1.
Moving to K1, the calculation for Noah Koda is actually quite elegant. It results in 0.
0, really?
Yep, 0. When we apply the formula using the degree N17 and that initial coefficient L0Q equals 18 from our polynomial, all the terms cancel out perfectly. It just collapses to 0.
Huh. Why is that significant?
It's significant because it means that when we eventually rewrite the polynomial using these new coefficients, the term with by 16, which corresponds to A0R, will completely vanish. That's an immediate simplification right there.
Nice. Okay, what about K2?
For K2, we find L11 S order 153. And interestingly, this S1R value corresponds directly to the L1Q coefficient in the original polynomial.
Ah, okay, so S1R equals L1Q to 153.
In this case, yes. And its exactness is just a testament to the formula's precision.
Gotcha. Keep going. K3.
For K3, we calculate many 2 on a 2. O is 1938. Now, this one is derived using a more complex combination of terms. It involves the initial coefficients L0q, L1q, and L2q, and their powers all interacting with those binomial coefficients and the original degree N17. The exact result pops out as 1938.
Okay, so they start getting more complicated to calculate, but the result is still exact.
Exactly. And as we continue this recursive process, the Skal values tend to grow, often quite dramatically in magnitude. For example, S3R is 37,944.
Okay.
S4R jumps to 674,424.
Wow.
S5R climbs into the millions. It's 12,150,196.
12 million.
And by the time we get to K8 calculating S7R, we're already looking at coefficients in the billions. Precisely 3,938,733,200.
Billions, just from applying this formula recursively.
Precisely. And here's where it takes a really significant jump in magnitude and sometimes changes sign too. For K9, the S8R coefficient becomes this colossal negative number over 5 quadrillion.
Quadrillion, you're kidding.
Nope. It's McCufferin 765,553,000,000, 70,380,523. And remember, this isn't an approximation. It's the exact, precisely calculated value down to the very last digit.
That's mind-boggling.
It is. And we also see subsequent values like S9Q, which is over negative 51 quadrillion, and S11R, which is over negative 20 quintillion. These are numbers that would utterly break traditional calculators if you tried to maintain perfect precision.
Okay, that's a lot of incredible numbers. And while we're not reading every single one out, the point here is absolutely crucial, isn't it? This recursive calculation of coefficients ensures that we are working with exact symbolic values, not approximations.
That's the core takeaway.
Every single digit in those massive numbers, like the quadrillions and quintillions you mentioned, is precisely derived. There's no room for rounding errors. This is the bedrock of Ezouidi's theorem.
Right. The computational power needed to actually perform these exact calculations with such huge numbers is immense, no doubt. But the theorem provides the elegant pathway for doing it systematically and exactly.
So once all these sick values are meticulously calculated, and the theorem gives us the method to do that, what happens next?
Well, once you have all 18 of these values from S1Q to S6, the original polynomial can be re-expressed using these new symbolic coefficients.
So you rewrite the whole thing.
Exactly. This transforms the original kind of unwieldy expression into a more structured form. And that structured form then paves the way for deriving the exact roots. It's like disentangling a complex knot into a series of perfectly straight lines ready to be measured.
Okay, show me. What does the 17th degree polynomial look like when it's re-expressed with its SK coefficients?
All right. You'll notice immediately, as we predicted, that the by 16 term, which corresponds to 0r, has indeed vanished because 0r was 0.
Nice simplification already.
Exactly. Now, while the full re-expressed polynomial still looks pretty daunting because of the sheer magnitude of some of those same values we just discussed.
Yeah, those quadrillions.
Right. The absolute T is that every single coefficient in this new form is known exactly. Here it is. Px. A, 0 is by 16 plus 153 by 15 plus 3794 by 16 plus 3794 by 20 plus 67 on 424 by 12 plus 12158 by 11 plus 39387 by 9 plus 5765553 523 by 8 518 490 9170 5230 523 by 8 Jeff plus 429 5739 4 plus 429 587 0 177 8451 0917331 by 4 plus 429 533 78 7131 77 x set minus 7390 52392 by 2 plus 4293 4 by 2 checks rate on 592 by 2 plus 3798 439 x plus 379 43910 5433390 samus of 0.
Precisely. And this revised form of the polynomial where the coefficients are now these exact split values allows for the final step, finding the roots.
Okay, the moment of truth. What are the exact roots?
The ultimate expression for the exact symbolic roots derives through this entire meticulous process, takes a form that might look complex at first glance, but it's incredibly precise. The source indicates a form like this: 1 plus 2 free c-squares together 29 times e2ki9.
Okay, let's unpack that a little. What does that actually mean? Especially that e part. Right, that e to the power of 2k9 involves complex exponentials. It tells us that the roots aren't just single isolated numbers. They're intrinsically linked by a common base structure, that part in the parentheses raised to the 19th power.
Okay.
And then they fan out, kind of like spokes on a wheel in the complex plane, determined by that exponential term where 8 goes from 0 up to 8. Each one is precisely defined. This structure ensures we capture all 17 solutions, including both their real and potentially imaginary components, without any ambiguity, without any need for estimation.
So it's not just a solution, it's a formula that generates all 17 exact solutions.
That's the idea. This form is a direct outcome of the recursive steps we followed.
Okay, this is really the key takeaway from this section then, isn't it? Ezouidi's theorem doesn't rely on numerical approximations at all.
Not one did.
The roots we've derived, represented by that formula, are exact. They're not subject to the error-prone calculations that inevitably come with numerical methods.
That's the monumental shift. It means that for this incredibly complex 17th degree polynomial, something that was once approachable only through imprecise approximations can now be fully and perfectly understood, down to every infinitesimal detail, because we're working with the exact symbolic values all along the way.
So we've tackled a 17th degree polynomial down its exact roots. That was already a massive challenge. But you mentioned earlier, what happens when we extend this method to an even higher degree? You hinted at an even more dramatic, almost unbelievable simplification.
Ah, yes, the 18th degree case. This is where the patterns revealed by Ezouidi's theorem become truly striking.
All right, let's take everything we've learned now and apply it to an even greater challenge, an 18th degree polynomial. Now, looking at the source, you'll notice it's remarkably similar in its initial coefficients and structure to our 17th degree beast. It's just extended by 1 degree.
Right, very similar starting point.
But there's a subtle yet really telling detail. Its constant term, the L17Q coefficient, is 0. This might seem like a small thing, but as we'll see, it has pretty profound implications when we apply the theorem.
Definitely. For this polynomial, our n value, the degree, is now 18, and that 0 constant term. It's often a crucial hint in polynomial problems. Sometimes what's missing from an equation can be just as significant as what's actually present.
Okay, now here's where applying Ezouidi's theorem to calculate those coefficients reveals something truly remarkable.
Yeah.
We're going to go through these values for this 18th degree polynomial. You're going to notice a striking, almost astonishing pattern emerge.
Okay, let's start the calculations again, this time for n18, following the same precise recursive formula. Just like with the 17th degree polynomial, for k1 we find s0r equals 0.
Okay, another 0 to start. So the by 17 term vanishes.
Correct. First term vanishes. Now for ko2, also, astonishingly, becomes 0.
0 again, 2 in a row.
2 in a row. The rigorous application of the formula, with all its binomial coefficients and interactions based on the original all coefficients, simply yields 0. This is already a strong sign that something unusual, something highly simplifying is happening here. The by 16 term will vanish too.
Okay, keep going. What about K3?
You guessed it. This remarkable pattern continues. For K3, S2R equals 0.
No way.
Yes way. And again for K4, S3R equals 0. This isn't just random chance, it's a direct result of this polynomial's specific coefficient structure interacting with Ezouidi's recursive calculations.
This is wild. How far does this go?
We see this incredible pattern hold for S4R, S5R, S6R, and S7R as well. They all evaluate precisely to 0.
Wait, so that's 0R through S7R. That's 8 consecutive coefficients, all becoming 0.
8 consecutive coefficients, yes. Think about that. 8 terms in the potential expansion of this massive 18th degree polynomial, each representing a complex interaction of previous terms. They just cancel themselves out to absolute 0 through Ezouidi's process. It's incredibly unusual and leads to a truly dramatic simplification.
That's hard to believe. What happens next? Does it stay 0?
Ah, but then the pattern shifts. For K9, we hit a significant non-zero term. S8R equals 486 themselves to 18 oro.
Okay, so it breaks the pattern. And that looks like a huge number again.
It is a massive negative number, over 48,000 multiplied by 18 raised to the power of 9. This is a crucial non-zero term that brings the xs term back into the equation. It's like the polynomial was mostly quiet for those first 8 terms, and then suddenly this one term roars back to life.
Okay, S8R is non-zero. What about S9R?
Following that, the pattern of zeros actually returns, almost as if the polynomial is tidying itself up after that one loud statement. S9R evaluates back to 0.
Back to 0, wow.
And this continues all the way through 16R. That's another 8 consecutive coefficients from S9R right up to S16R that remarkably becomes 0 once again.
So 8 zeros, 1 non-zero, then another 8 zeros.
Exactly. And then for the final coefficient, K18, we get the last non-zero term, S17R equals 488,618R18. This is the exact constant term in our re-expressed polynomial, and it's an astronomically large positive number.
This is just, what's utterly fascinating here is just how many terms zero out. It's almost unbelievable given You started with this complex 18th degree polynomial.
Right. 16 out of the 18 coefficients from 0 to 17, excluding S8 and S17, are 0.
And this isn't random, you're saying. It's a direct and precise result of the original polynomial's specific structure and the rigorous recursive calculations of Ezouidi's theorem.
Absolutely. This dramatic simplification is incredibly powerful. It transforms what looks like a daunting 18th degree polynomial into something far, far more manageable, practically just collapsing before our eyes.
So what does the simplified polynomial look like then?
Well, with most of those coefficients turning out to be 0, the re-expressed 18th degree polynomial simplifies dramatically from its initial intimidating form. It effectively collapses into just 3 terms: px by 18 r by 9 plus s17 r equals 0.
Wait, that's it? From 18 terms down to just 3 by 18 by 9 and a constant.
That's it, because all the other coefficients were 0.
And here's the truly elegant part, isn't it? The real aha moment for this specific example. Because of this specific extensive simplification, this 18th degree equation can now be viewed as a simple quadratic equation.
How so?
Well, instead of being quadratic in x, it's quadratic in terms of x roots. Think about it. If you let, say, y exude, then by 18 is just y. So the equation becomes y s8ry plus s17r is 0.
Ah, I see. It's quadratic and by 9. That's brilliant.
Right, and plugging in the exact S8R and S17R values that Ezouidi's theorem so meticulously calculated for us, the simplified 18th degree polynomial becomes by 18 plus 4, 8, 6, 9, 7, 8 by 9 plus 4, 8, 6, 6, 8, 10, IB 18 Oriole equals 0.
Okay. Now, because it's effectively a simple quadratic, just an xu instead of x, we can solve it directly using the good old quadratic formula.
The familiar Manny's quadratic 2a formula, that one.
That exact one. We just apply it to solve for y, which is x.
Okay, walk me through it.
First, we calculate the discriminant, often called delta, or in the source's notation, 1, 1. That's the B, 4, she part. So here it's 4, 101, 17. Plugging in the precise exact values we found for S8R and 17R, that becomes 408, 18R. And that simplifies exactly to 236,361, 200,689, a task in 4 to 5 and 17 tax 18, which gives a final discriminant 1110, 1 old on 18, 18 tes 9, 18,000, 18. Wait, let me recheck the source calculation for the discriminant. Ah, the source that's not no londo plus 4 and a 272 plus 461 and 6, 8 plus 4, 1 on 461 pounds, 18 on, well, plus 4 on board on 86 on 18 arco. Okay, that evaluates to total place 361 to or 872, 26 1 and 18, 217 are, oh wait, no, my apologies, it's negative. Every number in this calculation is exact though, 0 rounding error.
Got it. A huge, exact, negative discriminant. So the roots for by 9 will involve imaginary numbers.
Correct. From there, the solution for x sub o is straightforward using the quadratic formula, x sub o at 1, which is no o and o no.
Okay, so that gives us 2 exact values for x.
Exactly. And then, to find x itself, we simply take the 9th root of each of those 2 expressions.
The 9th root, okay.
And this step also involves incorporating those complex exponentials again, like we saw with the 17th degree case. This accounts for all 9 possible complex roots for each of the 2 xi solutions, giving us 18 roots in total. So the exact symbolic roots for x take the form dode, no date, ana bi ou 19, 2k9.
Wow. So even though it started as an 18th degree polynomial, Ezouidi's theorem collapsed it into something solvable with the quadratic formula, and then we just take the 9th root.
In this specific case, yes. It demonstrates the remarkable consistency and power of Ezouidi's theorem. It leads to exact, unapproximated roots, even for extremely high-degree polynomials that, at first glance, appear absolutely intimidating and classically unsolvable using standard formulas.
And the source mentions sigma formulas, too.
Yes, the sigma formulas provided in the source material also align perfectly with these exact roots, which just confirms the method's internal coherence and correctness. It provides a clear, precise path from a complex, daunting polynomial straight to its exact solutions, completely bypassing the ambiguities and inherent limitations of numerical methods.
Okay. We've just taken quite a whirlwind tour through Ezouidi's theorem.
Yeah.
From the daunting complexity of that 17th degree polynomial to the surprising, really dramatic simplification of the 18th degree one. And it all seems to circle back to one core message, doesn't it? A fundamental shift in how we might approach these kinds of mathematical problems.
Yeah.
Precision over approximation.
That's exactly right. Unlike traditional methods, which, as we've discussed quite a bit, often have to resort to numerical approximations, Ezouidi's theorem provides a precise symbolic solution.
And that ensures
Right.
what exactly?
It ensures that the roots we obtain are exact. They're not subject to the accumulating errors that inevitably arise with numerical methods. And this isn't just, a marginal improvement, it's a fundamental shift from settling for a close enough to achieving perfectly precise. It means we can potentially work with the truth of a problem, not just a close estimation.
And this leads us back to what is perhaps the most profound implication of this work: the reevaluation of what we even consider unsolvable in mathematics.
Right.
The source material directly asserts, and it's worth repeating, contrary to Abel's assertion, my method demonstrates that even polynomials with radical roots can be solved exactly.
It's a bold statement.
It really is. So if a new theorem can so fundamentally redefine the solvability of complex polynomial equations, what does that actually mean for the established boundaries of mathematics? When a new method provides precise, solvable roots for problems that would otherwise have been deemed impossible for generations.
Well, it's a direct challenge, isn't it? A challenge to these long standing limitations in classical algebra. It suggests that what was once seen as an impenetrable wall might actually have a hidden doorway we just hadn't found yet.
Hmm.
Philosophically, it kind of forces mathematicians to re examine some deeply held beliefs about the absolute limits of exact solutions. It opens up the possibility that other mathematical impossibilities might simply be waiting for a fresh perspective, a new set of tools to reveal their underlying exact solutions. It's really about being able to work with the truth of a problem, as you said, not just a close estimation.
And let's think about the real world implications for a second. If such complex polynomials can now potentially be solved exactly, what does this unlock for fields where precision is absolutely paramount and where high degree equations are actually pretty common?
But cryptography?
Yeah, cryptography.
Yep.
The security of vast amounts of data often relies on the assumed difficulty of solving certain mathematical problems, right? Like factoring huge numbers or breaking certain types of equations.
Mm.
If a method like this can provide exact solutions where none were thought to exist, or where approximations were the only way, it could genuinely revolutionize cryptographic design. It could lead to new, maybe more robust, or even fundamentally different security protocols.
That's a huge potential impact. Or think about advanced engineering. Imagine designing, say, the next generation of aircraft or spacecraft where every nanometer of precision matters.
Or new materials.
Exactly. New materials with perfectly predictable quantum properties. Being able to solve the underlying high degree equations with exactness rather than approximations could allow for much tighter tolerances, more efficient designs, perhaps completely new functionalities that were previously unattainable just because of the cumulative errors you'd get with numerical methods.
It could really refine things.
It could potentially allow us to design systems with much tighter tolerances, or maybe uncover subtle relationships that were previously just obscured by those accumulated rounding errors.
And then there's theoretical physics. I mean, many of the fundamental laws of the universe are described by incredibly complex equations, often high degree polynomials or related forms.
Very true.
What if working with exact values instead of approximations could lead to new discoveries? By revealing subtle relationships or maybe emergent phenomena that were previously hidden simply by the imprecision of the older methods.
It could certainly accelerate our understanding of everything from, say, particle interactions to the complex dynamics of black holes, simply by allowing physicists to work with the perfect truth of the numbers involved. It could fundamentally change the landscape of research and application in these fields.
And what underpins all of this potential, as we've seen in our examples, is the sheer power of the theorem's recursive structure. That seems to be the key.
Absolutely. The systematic nature of Ezouidi's approach is its true marvel.
That's right. As we discovered, the roots are derived recursively. We solve for them step by step. These formulas systematically break down the polynomial into manageable components, allowing us to derive exact symbolic values instead of approximations.
Mm.
This methodical, precise approach, without relying on any numerical estimations at all, is truly the marvel here. It's a testament, really, to the elegant solutions that can emerge just from rethinking fundamental mathematical problems and maybe pushing the boundaries of what's traditionally been considered possible.
It's the elegance of that recursive breakdown that seems to make the intractable, well, attractable. It really demonstrates how deeply intertwined the structure of a problem is with the tools we actually use to try and solve it.
So you've just taken a deep dive with us into Ezouidi's theorem, a method that seems to provide a stunningly precise way to find exact symbolic solutions for high-degree polynomials, and in doing so, directly challenges centuries of mathematical thought about what's actually possible.
It really makes you wonder, doesn't it? if a new theorem can so fundamentally redefine the solvability of these complex polynomial equations problems
Hmm.
that were once considered forever out of reach for exact formulaic solutions, what other impossible problems might be out there
Yeah.
in mathematics and science, maybe even in everyday life? Problems that might just be waiting for a fresh perspective or a new set of tools to reveal their exact, precise solutions.
What else are we currently approximating, maybe without even realizing it, that could actually be solved perfectly if only we had the right key to unlock its hidden exactness? Something to chew on, definitely.
Thank you for listening. This is an example of 17-degree formula equation. We already solved it by extension. We extend the 17-degree formula equation to 18, and we find out, let's say, the x roots of the new 18-degree formula equation. Then we go back to the recursive formula, and we put the alpha substitute k from 0 to 17 equal to 0 to 42 plus sk from 0 to 17 over 18. Then we move to write, let's say, the relationship between xk dash and xk. Xk dash means the x roots of the new 17-degree formula equation, and xk means the 17 x roots of the new 18-degree formula equation. Thank you for listening, and see you next time. Thank you. Goodbye.